Hi everyone, and welcome to the fifth lecture of digital communication titled Delta Modulation.
Last lesson we started this.
Exactly, but quickly I'm going to remind you of what we have taken briefly from the previous lecture and then continue from where we left off. So basically, if you remember with me when we talked about pulse code modulation, we said that one of the key issues that you may encounter while you are doing pulse code modulation or analog to digital conversion is the fact that sometimes the amount of generated data is huge, and this results in the need to have large memory size and also large bandwidth to transmit your signal. And this costs you money in either way, whether you in terms of memory or in terms of bandwidth. So there are cases where you need to transmit your analog signal with minimal amount of data bits. So this is where we need delta modulation. With 1-bit quantization, you can send your analog signal, and it's really featured by its simplicity. That's why we will study in this lecture deeply delta modulation and its features, its plot diagram at the transmitter and receiver, and its problems and drawbacks, and how can we encounter them, and some mathematical formulas related to this. So delta modulation basically is a simple, not sophisticated modulation scheme used to transmit 1 bit per sampling frequency. At each sample you are sending 1 bit. In delta modulation, the analog information signal is usually oversampled before you start your delta modulation process. And the reason for that is to increase the correlation between adjacent samples, and you can make sure that the step function you have can follow up with your analog signal. And this is done to permit the use of a simple quantization strategy where you can use 1 bit for each sample. So in its basic form, delta modulation provides a staircase approximation to the oversampled version of the message signal as shown below. Here you have the analog signal that you want to transmit over your medium, and to encode this using delta modulation, the basic rule is this: if the signal is going up, you go up by delta at each sample, at each input sample, and when the signal go down, you go down by delta at each input sample. So basically you try to come up with a step function that can follow the characteristics and the variation of your input signal. So at the end of the day, you will get a sequence like this, which is binary sequence, zeros and ones, that you can transmit over the channel. The difference between the input signal sample and the staircase approximation is quantized into only 2 levels, plus or minus delta, according to the level of your current input signal. If the current input signal sample is greater than the previous sample, then the delta modulator generates plus delta. Otherwise, it generates minus delta, which is the vice versa case. The discrete time equation which describes delta modulation can be written as follows: E of n is equal to the value of the message signal at time equal n minus the quantized value at the previous time, n minus 1, and consequently, the quantized error becomes delta multiplied by sign E of n, where sign, everybody knows how to draw sign. Suppose you have this x-axis and y-axis. Sign is a signal that has this form. This is in minus delta, for example, and this is plus delta. So this is the plus delta and this is the minus delta. Basically, sign function is 1, but you multiply it by delta because your step size is delta. So the quantized message at time equal n becomes the previous quantized message plus the error. The error is the difference between the staircase function and the actual value of the message. This is the error. Where En is the error signal representing the difference between the present sample and the latest approximation. EQN is the quantized version of the error. So this is basically what's delta modulation, and as you can see, it's very simple, straightforward, not so complex, and you can generate less number of data to transmit your analog signal. So its main feature, simplicity. Also, it has low overhead signaling, where you only send 1 bit per sample. You don't need to send many bits per sample like the case of pulse code modulation. So delta modulation, the delta modulator can be constructed from the discrete time equation according to the block. You have the sampled message signal here, and you have comparator. The comparator is like the differentiator. It works like differentiator, because in differentiation you have your current value minus previous value over the step. It's the same here. And this results in 1 bit quantizer, and then you take the previous value here and feed it back, delay it by 1 unit of time, and then take it to the comparator to take the second value, and so on and so forth. Basically, this block diagram represents the process in which you generate your delta modulated signal. The demodulator on the other side, at the receiver side, exactly do the reverse. For example, you receive your message 0 and 1, 1 and 0. So when you see 1, this means that you go by plus delta. When you receive 0, you go by minus delta. And then you smooth. You pass the signal to low pass filter so that you can get smooth received signal. This can be achieved by summing the received bit stream as described by the following equation, which is again the signal value used at the transmitter, which is representing plus and minus, and with delta it becomes plus and minus. And at each value, the value of the message at each time is the summation of all the previous values, multiplied by delta. For example, suppose plus 1, plus 1, plus 1, and you need to determine the value of the message at t equal 3. So it's the summation of the previous ones. Yes? So you will have a stair function of 3 steps. Yes? Because it's going up. If it is 0, then minus 1, and you go minus 1 by the number of steps. This is I from 1 to n represents actually the time, the x-axis. The waveform results that the receiver contains a staircase approximation. So at the end of the day, when you receive a sequence like this is the digital sequence that you transmitted, and basically since you are transmitting baseband signal, this becomes like if you are using unipolar non-return to 0 coding, then this becomes like this. This is the signal, the electric signal that you transmit over your channel, and when the delta modulation demodulator receive this, the receiver, this is 1, then this is delta, this is another 1, this is delta. Of course you just, and then minus, when minus you go by minus delta, and so on and so forth. At the end of the day, you will end up having what? Stair function. Yes? You pass this to low pass filter. After the low pass filter smoothes the transition and becomes, you get your analog signal back at the receiver side. Of course, the stair function, this results in distortion. We call it high frequency distortion, can be removed by passing your signal into low pass filter. The demodulator can be constructed from the discrete time equation describing the demodulator according to the block diagram shown below. This is the block diagram that you need to demodulate your delta signal. Basically, you have here the zeros and 1 and zeros. After the decoder, you decide whether it's plus delta or minus delta. Yes, according to 0 and 1, and then you pass it. This is accumulator actually. This is the summation. This diagram is the summation in the equation, the previous equation. For example, when you are at point at t equal 4, you sum all the deltas before 4, so that you get the value at 4. Yes, because it's a stair function. How can you get the value at 4 if you don't know the value before 4? 1, 2, 3, 4. Accumulative. And then to get rid of the high frequency distortion, you pass your signal to low pass filter and you get your message signal back. Quantization errors in delta modulation. Now we talked about the advantage, the benefits, the merits, the pros of delta modulation, and we have all agreed that it's a great modulation scheme, can reduce the amount of data you need to transmit and save on your memory, and it's really something that you need to do in communication in certain cases. However, in spite of its many advantages, there are cases where it can really not perform well. And the reason for that are two. First, delta modulation is subject into two quantization errors. The first one, we call it slope overload distortion, and the second one, we call it granular noise distortion. I need from you to understand what's the reason behind these two problems and how can we solve them. So, slope overload distortion. Why do we have slope overload distortion? When slope overload distortion happens, when your step size is so small to a level that it cannot follow the variation and the slope in your message signal. See, your delta is small compared to the variation, the slope of your analog signal. So, the staircase function will not be close enough to your analog signal, so it will cause some error. This gap between the actual signal and the staircase is error basically, because you are getting a stair function which is a little bit far away from the actual signal, and all this shaded area is error. So this is the cause of the first problem. Overload, slope overload distortion happens when you use low step size, short step size that cannot cope up or follow the variation or the slope of the actual analog message signal. What about the granular noise? Granular noise happens when the step size is large, more than the slope of the message signal. So when you come here, this is the slope here almost like 0. There is no slope actually. And still your delta is going up and down, not able to decide whether it's plus delta or minus delta. All this is noise, too much noise. You must reduce it. You must reduce the shaded area, because the shaded area is noise. So, having talked about these two problems, now you are expert in determining the cause of slope overload distortion and the granular noise. This we call it granular noise, and this we call it slope overload distortion. Then the question, if we have such problems, what can we do to overcome them? The first thing for slope overload, if I ask anyone among you, what can you do to overcome the slope overload distortion? Quickly. What would be the solution for that? Increase the step size, increase delta. Instead of making delta small, make it a little bit larger so that it can follow the changes in your message signal. So here delta, you will increase it. When you increase delta, for example, this becomes delta. This is the step size of the new delta. Suppose that, let me erase all these mess. The mess here, where is the eraser? Here, Control Z is actually. So suppose we want to solve this problem, what do? We just increase the step size. When we increase the step size, the new stair function becomes, this is the new step size. And then you go another delta. Now it's larger. See, it's becoming closer. It's becoming closer to the function. Yes, we solved it. You see the shaded area here between it's less than the previous one, and therefore we have less noise, less error, and your stair function will represent your message in a much better way. What about the granular noise? What's the solution? Propose me a solution to solve it. Reduce the step size. Reduce the step size here instead of making it shooting like this and creating too much difference between the delta and the actual message. You just reduce this delta when it reaches to a slope equal to 0. Reduce delta. So basically, this is what you exactly need to do in order to solve these two problems. You understood the reasons, the causes of these two problems, and also how to solve them. So you end up, by solving these two problems simultaneously, you end up having what's called adaptive delta modulation. Yes, adaptive. What does adaptive mean? Means you are changing the step size according to the characteristics of the function. So you cannot solve these two problems when one fixed step size, no matter what you do. Absolute statement you cannot do with one step size. You must use adaptive step size. When you have a slope overload, you must use larger step size, and when you have a granular noise, you must use short step size, so that you can solve the two problems simultaneously. So suppose you have a case or a problem, and I tell you what's the rule that I can adopt in the design of delta modulation so that I can avoid overslope distortion. Is there any such a rule that can help me overcome this problem? I tell you yes. Think with me, like we want to derive this equation logically. Don't worry about the equation. This equation says slope overload distortion can be avoided if the step size delta is selected according to the following equation. From where this equation came? We need to understand this by logic, by understanding the logic. Go back with me here. Look here. What would be the rule that makes sure that we don't have slope overload distortion? If we make the slope of the stair function close to the slope of the actual message signal, then you won't have that problem. Yes or not? What's the slope of the stair function? Tell me. The slope is actually the difference in y over the difference in x. What's the difference in y? Delta. The difference in x, ts. This should be approximately equal or larger so that you can avoid the slope in the message. What's the slope of the message? If I give you any random message, any random signal, any random voice or data or whatever, what's the slope of that? It's derivative. If you don't have linear drawing and this, if you don't have linear function, you cannot say difference. The difference in general is derivative. So it becomes the derivative delta over delta t of the message, m of t. So this is the rule. Did you understand how we derived it? It's not written in the slides, not written even. So here we come back to this rule. Everybody understands with me this rule now? Do you need to memorize it? You don't need. You just understand it. You know from where it came. So delta over ts must be greater than or equal at least the derivative of the message signal itself. So this is with respect to slope overload distortion. What about granular noise? Granular noise, we said it happens when the step size delta is too large relative to the local slope characteristics of the input signal. This would cause the staircase approximation to hunt around the relatively flat segment of the input waveform. You will have too much fluctuation with too much difference from the actual message signal, resulting in some error. And this causes granular. Sometimes there are books and papers that call it idle noise or granular noise. Now these are the disadvantages of delta modulation. The main disadvantage of delta modulation scheme is the presence of, beside the previous problems that we talked about, there is another problem related to delta modulation, which is Anybody can guess exactly from the ones who are working on projects related to modulation? The ones who studied number modulation, index modulation. What's this? What we call this? Since the receiver decides based on the previously decoded samples, then the current sample that I need to demodulate depends on the previous ones. If it depends on the previous ones, or this we call it propagation. It can cause propagation error. If you make an error in the first one, this affects the second, third, fourth, and so on and so forth. This we call it error propagation. A cumulative error in the demodulated signal. This comes from where? From where is this comes? From this equation, the demodulation equation, where I told you to decode the third sample, you need to know its value. You need to know the value of the second and first. And then you sum them all so that you can get the final. And this is exactly where we are. Yes, we call this, although I didn't write it here, we call it error propagation. A cumulative error in the demodulated signal. This problem, we can solve it by using a delta sigma modulator. Delta sigma modulator integrates the signal, integrate the signal before you start performing delta modulation. In delta sigma modulator, the input signal MFT will be integrated prior to delta modulation. The use of integration in this manner described here has the following beneficial effect. What's the effect of using integrator at the input of your delta demodulator or delta modulator? What's the effect? What benefit you would gain? The low frequency content of the input signal will be pre-emphasized. The low frequency content when you integrate will be enlarged. And this can solve this problem, the error propagation. Yeah, I mean, what basically does the signal usually, if your signal before was this, let's say, yes, everybody with me? Let's say your signal is linear. After you integrate it, it becomes like this. Oh, so what happens here? If you integrate this again, becomes, so what happens here? Usually the slope becomes sharper. When the slope becomes sharper, what will happen? Your summation will depend on lower number of values, yes? For example, this depends on how many values from here to here, like maybe 10, but this 5, but this maybe 3. So the less number of values you depend on previously causes less error. True or not? Did you understand? Did you get the logic? You don't understand these things from the presentation only, or even from the book. We are together analyzing how the math affects the physical phenomena of the demodulation, and accordingly you can understand and relate things to each other. Yes? Everybody understand? Everybody agrees? Anybody wants to ask? Anybody wants to give new ideas? What can we do else? Maybe there are some other ideas that you can do to overcome this problem. So up until now we have 3 problems with delta modulation, and we know how to solve all of them. And we know the logic behind that. Is that true? We know how to solve them. Yes? We know. Delta sigma modulation, increases the correlation between adjacent sample of the delta modulator input. This is theoretically, which tends to improve the overall system performance. This is what's written in the book and says, but why? Why? Mathematically, tell me in the language that I understand why this happens. So, and this reduces the variance of error signal at the quantizer input. Design of the receiver is simplified. For example, all what you need to do when you have delta sigma modulator is to put this integrator at the beginning. And since integration a little bit is a complex process, complex computational process actually, not like, because integration is basically what? Summation. Summation, each sum is a logic circuit, while derivative is subtraction. What's subtraction? Subtraction is comparator. Comparator is simple to design, just comparing. That's why anything that has comparator, we say it's low complexity structure. Anything that has integration, we call it high complexity structure. So the previous block diagram, we can simplify it more if the signal is first differentiated and then applied to the input of the integrator. So to simplify things, that's why I told you that differentiator is much simpler than integrator, and this is where we utilize this fact to simplify the design of delta sigma modulator. Yes, first you do this. This is what differentiator. The comparator is derivative, basically, and after that the integrator. And since the comparator is just minus the that's why it's really simple and easy. Yes. I hope you understood everything related to delta modulation and you become expert in designing the modulator and demodulator, understanding the advantages of delta modulation. Where do we use delta modulation? When do we use it? And why do we use it? Why do we use it? It's simple. It generates 1 bit per sample. 1 bit. So it saves power, it saves processing, it saves memory, it saves bandwidth. All of these are advantages. Low overhead signaling, all of these you can list them and justify them and understand them exactly how they relate to your practical life. And what are the problems? The problems are basically three key problems. The first one, overload distortion. What's the reason of that and why it happens and how to solve it? Granular noise. What's the reason of that when the step size is so large with respect to the slope? And how to solve it by using adaptive delta modulation, used different step size according to the slope of your message signal. And last problem is error propagation. How to solve it? By integration, so that you can increase the slope of your function and make your current value dependent on less number of previous values. This is the summary of our lecture up until now, and we learned the law, that the formula that we need to use so that we can avoid overload distortion. Now it's time to apply what we have learned in practice. We have some questions. We need to solve them together so that we basically understand exactly what we are talking about and test whether we know what we have taught and what we have explained or not. So the question says, consider we have a sinusoidal wave of frequency FM and amplitude AM, which is applied to a delta modulator of step size delta. So these parameters you need to be careful about, you need to highlight them, and so that you can use them later on in your solution. The question says, prove that the slope overload distortion will occur if AM is greater than. So this is what I want you to prove in this question. So where TS is the sampling period and the maximum, so the question says, then what's the maximum power that may be transmitted without slope overload distortion? Great. So the question is asking, what would be the maximum point at which there will be no slope overload distortion? So you reverse the formula. To avoid overload distortion, what do we say? Delta, the slope of the stairwise signal, which is delta over TS, must be equal or bigger than the derivative, delta, M over dt, and this is function of t. So now he says, slope overload distortion will occur if. So if you don't satisfy this, slope overload distortion will happen. Then this means that you need to reverse this. Yes, actually, the complement of this, which is less. So in this case, delta over Ts is less than d over dt of m of t. Great, up until now, you understand why we reverse this? The complement, because it talks about the opposite. This is the case, this is the condition to avoid overload distortion. This is where overload distortion can happen. You have sinusoidal signal. What's the sinusoidal signal? You write m of t is equal to am sine 2 by fm t. I need to find the derivative of m of t. So what's the derivative here? Am 2 by fm cosine 2 by fm t. Great, up until now. This is this side. This is this side. So I have delta over Ts. This must be less than this. So if you put am, the core of the equation, on the right side of the equation, am becomes am here, yes? Am greater than delta over Ts 2 by Fm. Is this equation the equation we have here? Is it the same? Yes. It's exactly the same, but the opposite, written the opposite. Writing am in the left side, here am in the right side. You can just put it the opposite. So we proved. Did you see how we proved it? It's simple. So don't get scared when someone says prove. It's just with the logic, you start with what you know and you get to the final answer. What's the maximum power that may be transmitted without slope overload distortion? The maximum power, if this is the amplitude of your sine wave signal, what's the power? If you have 1 ohm resistor, am square over 2. Yes, this is the power. So what you need to do is substitute the value of am in terms of delta Ts Fm here and get the result. And if I give you values and multiple choice or circle question, you can substitute these values and then find the answer. Great. Is that beautiful? Is that understood? So this is the first question. I put the solution here again for the ones who didn't focus with us in the previous question. But I recommend you to follow up with me while I'm explaining so that you don't need to study at the day of the exam. Yes? We just know now. Any questions similar to that, you can solve it, of course. Now, what else we need to... There is another example that we will conclude our lecture with. The example says that assume we have a linear delta modulator which is designed to operate on speech signals limited to, this is the demodulator, the speech signal has frequency 3.4 kilohertz. The specification of the modulator are as follows. Sampling rate is equal to 10 F Nyquist, where F Nyquist is the Nyquist rate of the speech. Step size is this value. Now I'm giving you specific value. The modulator is tested with 1 kilohertz sinusoidal signal. Yes? So the modulator basically, originally, it was designed for a speech signal. Focus with this. Yes? Now, they want to test the modulator for a signal which is not speech. It's a different signal that has a different frequency. It was a sinusoidal signal basically, 1 kilohertz. Determine the maximum amplitude of this test signal required to avoid slope overload distortion. What would be the maximum amplitude of this signal so that you can avoid overload distortion? You tell me delta over Ts must be greater than delta MT. What's MT here? The test signal, which is sinusoidal with 1 kilohertz. M of T is equal to, here you can come here and say that M of T is equal to AM, which is, I don't know its value, the question is asking about it, multiplied by sine 2 by, multiplied by 1, 2 by T. Yes? You derive this, after you derive this, you get 2 by AM multiplied by cosine, and since you take the absolute value, the maximum, you just put 2 by AM. Yes? Now, what's delta? Delta is this. You put delta 100 millivolt over TS. What's TS? 10 F Nyquist. F Nyquist of what? Of the speech signal. So, this is TS. TS is equal to 1 over Fs. This is the sampling rate Fs, which TS is equal to 1 over Fs. Fs 1 over Ts. So here I have Ts, which is equal to 1 over 10 F Nyquist. F Nyquist is equal to 2 multiplied by 3.4. So you have 10 multiplied by 2 multiplied by 3.4. So we are everything is known in the equation, just we have AM not known. So you can easily calculate these numbers and find the value of AM that you would need in order to avoid overload distortion. This is the detailed solution. You can look at it at home and ask me any questions if you didn't understand it or you have problems or anything like this. So thank you everybody for listening to this lecture about delta modulation, and meet you next time